The James Webb Telescope has recently made groundbreaking discoveries that challenge and expand our understanding of the cosmos. Through deep observations of the earliest galaxies, it has revealed phenomena that suggest the possibility of another universe beyond our own, or at the very least, that our universe's infancy might differ vastly from anything we previously imagined. Data from the James Webb Telescope focused on the most distant reaches of the universe, places where light has traveled over 13 billion years to reach us. These images capture a time when the universe was in its earliest stages, only a few 100 million years after the Big Bang. However, what scientists are observing defies their expectations. These findings include ancient galaxies that seem unusually massive, structured, and even chemically evolved for such an early epoch in cosmic history. The sheer scale of these galaxies and the presence of elements like carbon and oxygen suggest that stellar processes were already active, indicating multiple generations of stars within these galaxies. This revelation has astronomers questioning the accuracy of the standard cosmological model and wondering whether something fundamental about our understanding of the universe is amiss. The universe, according to long-standing theories, began approximately 13.8 billion years ago in an event known as the Big Bang. Since then, scientists believe it has expanded and evolved according to predictable laws and models that explain how galaxies, stars, and planets came into being. Observations by the Hubble telescope helped refine these theories, allowing scientists to view galaxies as far back as 11 billion years. However, the James Webb Telescope's unparalleled capability has pushed this limit even further, achieving redshift observations reaching as far back as 14.32%. For decades, astronomers have theorized that after the Big Bang, the universe went through a dark age, a period during which no stars or galaxies existed and light had not yet filled space. This phase lasted for hundreds of millions of years, during which the universe was opaque, filled with neutral hydrogen gas, and devoid of visible structures. According to conventional understanding, it was only after this dark age that stars began to form, eventually leading to the first galaxies and cosmic structures. But Webb's observations disrupt this sequence. The telescope has captured images of galaxies that appear to have existed even before this dark age, raising profound questions about how such structures could have formed so early. The presence of these massive galaxies challenges the notion that early galaxies should be smaller and less evolved if our theories are correct. Deeper observations should reveal progressively younger, smaller, and simpler galaxies as we peer further into the past. Yet the Webb telescope shows fully formed complex galaxies in these early epochs. This paradox has led some scientists to consider radical possibilities, such as the existence of another universe interacting with ours, or that we are looking at regions of the cosmos where different physical laws apply. These findings push the boundaries of cosmology, leading researchers to consider if the very nature of physics might vary across space and time. The differences observed in these ancient galaxies suggest that the laws of physics as we know them may not be as constant as previously thought. For example, a recent study published in Astrophysical Journal posits that gravity might have been about 1% weaker in the early universe on very large scales. This theory was developed after researchers examined data from the cosmic microwave background, CMB, which is the faint radiation left over from the Big Bang. The CMB has been instrumental in helping scientists understand the infancy of the cosmos, including the distribution of matter and energy in those early moments. Adjusting Einstein's equations to account for a weaker gravitational force helped the scientists align their theoretical models more closely with Webb's data. Einstein's theory of relativity has provided a foundational framework for understanding the cosmos, from the vast structure of galaxies to the mysterious phenomena of black holes. Central to this theory are the interwoven concepts of space, time, and gravity, which Einstein demonstrated to be deeply interconnected. This framework has shaped our interpretation of how the universe evolved, including the formation and movement of cosmic structures over billions of years. By accounting for gravitational forces, relativity has helped scientists explain how galaxies cluster, how stars orbit around each other, and even how light bends in strong gravitational fields. However, recent astronomical observations, particularly from the James Webb Space Telescope, suggest that certain cosmic conditions in the universe's infancy may not align perfectly with predictions based on Einstein's theories. This has led scientists to propose the possibility that relativity might require adjustments to accurately describe the early universe. For example, some researchers are exploring whether the force of gravity may have been weaker in those early cosmic stages. This hypothesis, though still speculative, could profoundly alter our understanding of how large-scale structures in the universe came into existence. If gravity were indeed weaker at that time, this would change the way matter clustered and coalesced to form galaxies, stars, and other cosmic bodies. A weaker gravitational force could mean that early galaxies may have evolved more slowly or differently than they would under the stronger gravitational pull we observe in our current universe. It could also imply that black holes, known for their intense gravitational fields, might have formed in different ways or at different rates than previously assumed. Such a shift in gravity strength might explain why some ancient galaxies observed by the Webb telescope appear more massive and evolved than expected for their age. Given current cosmological models, reconsidering gravity's role in the universe's early days would not only lead to a better understanding of cosmic evolution but might also inspire new approaches to physics itself. If relativity's predictions don't fully account for these early conditions, physicists may need to develop expanded or alternative models, reshaping our understanding of how the universe has come to be. Another aspect of the recent discoveries that challenges existing models is the non-uniform expansion of the universe. Observations show that the universe is not expanding at a single consistent rate everywhere, a discovery with wide-ranging implications. Traditionally, astronomers have measured this expansion using the cosmological constant, also known as dark energy, which is believed to drive the acceleration of the universe's expansion. However, data from Webb indicates that dark energy may not be constant. Instead, it appears to vary in strength depending on the location. This inconsistency in the universe's expansion rate raises questions about the true nature of dark energy and suggests that our model of the universe's evolution may need to be revised. One particularly fascinating theory to explain these discrepancies is that of a multiverse. Some scientists suggest that our universe might not be the only one. Rather, it could exist as part of a multiverse, a collection of universes that formed in parallel or in close proximity.
If our universe popped into existence near another universe, it is possible that they could have interacted in some way. Such an interaction might explain why we observe regions with differing physical laws or massive galaxies appearing earlier than expected. The hypothesis goes that if two universes collided during their formation, it might have introduced variations in physical laws across our universe, creating regions with differing densities, rates of expansion, or gravitational behaviors. This multiverse theory could account for why some parts of the cosmos seem fundamentally different from others. For instance, if the southern part of our universe were governed by slightly different physical principles than the northern, this might explain the asymmetrical expansion and unexpected structures. These ideas are speculative and difficult to test directly, but the Webb telescope's findings lend some credibility to these theories by challenging the completeness of our current models. Observing the first billion years of the universe's history has been a long-standing goal for astronomers, as this period holds the key to understanding galaxy formation, star formation, and the development of black holes. The James Webb Telescope has pushed these efforts further than ever before. With its unprecedented sensitivity and resolution, Webb has brought us closer to observing galaxies as they were when they first formed. However, the unexpected discoveries have left scientists reevaluating the assumptions underlying the standard cosmological model, which posits a linear, predictable evolution of the universe based on known physics. The latest findings have created excitement and controversy within the scientific community. Some researchers are thrilled at the prospect of revising theories and embracing new models, while others urge caution, emphasizing that more data and analysis are needed before drawing definitive conclusions. Nevertheless, one thing is clear: the Webb telescope has opened a new era of discovery, and its observations are leading us to reevaluate almost everything we thought we knew about the early cosmos. Another line of evidence that has prompted reconsideration of the universe's early development is the detection of carbon and oxygen in these ancient galaxies. Typically, these elements are formed in the interiors of stars and dispersed when the stars explode as supernovae. Finding these elements in galaxies only 350 million years after the Big Bang suggests that multiple generations of stars had already formed and died, seeding the universe with these essential elements. This finding is particularly surprising because, according to conventional models, galaxies this young should not have had enough time to undergo such rapid evolution. This rapid evolution implies that either star formation processes were somehow accelerated in these early galaxies, or that conditions in the early universe allowed for star formation on an unprecedented scale. Either way, the presence of such complex chemistry so early on raises intriguing questions about the potential for life-bearing conditions to arise in the universe's infancy. If stars and planets could form and evolve quickly enough to create the building blocks of life, then it may be possible that the conditions for life appeared far earlier than scientists previously believed. With its ability to observe at high redshifts, the James Webb Telescope is likely to continue providing insights into these early epochs. Scientists are hopeful that it will soon capture galaxies from an even earlier period, potentially reaching a redshift of 20. Such observations would allow astronomers to look back to within a few 100 million years of the Big Bang, an era that is still largely uncharted. However, if Webb continues to find massive, mature galaxies at these distances, it could further challenge the Standard Model, which suggests there is a limit beyond which galaxies and stars should not exist. This boundary, theoretically speaking, is tied to the dark ages of the universe, but Webb's observations suggest there may be more. To the story. These discoveries are forcing scientists to entertain the idea that the universe's early conditions could have been governed by different principles than the ones we see today. Whether due to weaker gravitational forces, as some have theorized, or due to entirely new physics, as suggested by multiverse theories, these findings imply that there are fundamental mysteries yet to be solved. The cosmic evolution that took place in the universe's first billion years may have been shaped by forces or interactions that are not present or are diminished in the universe today. The James Webb Telescope's images have proven to be both inspiring and provocative, reshaping our understanding of the cosmos while also exposing the gaps in our knowledge. These findings suggest that we are on the verge of a paradigm shift in cosmology. With each new image and piece of data, we gain a clearer picture of the early universe, but we also confront new puzzles that may lead to the revision or even replacement of long-standing theories. The James Webb Telescope is not only expanding our view of the universe, but also our understanding of its fundamental nature. Its observations are pushing scientists to think creatively and explore hypotheses that were previously speculative. Whether it is the presence of another universe, variations in fundamental physics, or a redefinition of cosmic evolution, these discoveries herald a new era in astrophysics. As we continue to unlock the secrets of the cosmos, Webb's data will undoubtedly play a central role in redefining our place in the universe and our comprehension of how it all began. In addition to its groundbreaking discoveries, the James Webb Telescope is also enhancing our understanding of the formation of elements in the universe. The detection of heavier elements such as iron, nitrogen, and even trace amounts of other complex molecules hints at a rich and diverse chemical landscape in the early universe. This complexity suggests that star formation and supernova activity may have occurred much earlier than previously thought, fundamentally altering our models of stellar evolution. Moreover, the implications of Webb's findings extend beyond cosmology and astrophysics. They may inform fields such as planetary science and astrobiology. For instance, the presence of essential building blocks for life, like water and organic compounds, detected in distant galaxies raises the possibility that habitable conditions could have formed much earlier than the emergence of life on Earth. This insight could shift the search for extraterrestrial life, prompting scientists to look for biosignatures in regions of the universe that were once considered too young to host life. Furthermore, as the telescope continues its observations, researchers are examining the potential impact of cosmic events such as gamma-ray bursts and the merger of black holes on the evolution of galaxies. Understanding these phenomena could provide insight into how catastrophic events influence star formation and the distribution of elements across the cosmos. These high-energy events may trigger new cycles of star formation, effectively seeding the universe with the ingredients necessary for life.
The advancements made by the Webb telescope also encourage a reevaluation of dark matter and dark energy, two of the universe's most elusive components. By mapping the distribution of galaxies and their clusters with unprecedented precision, scientists are gathering data that may reveal how dark matter influences galaxy formation and clustering. This information could lead to revised models that better explain the dynamics of the cosmos. As the telescope captures data across different wavelengths, its multifaceted approach allows for a comprehensive analysis of cosmic phenomena. This capability positions Webb as a key tool in unraveling the mysteries of our universe, providing a wealth of data that will fuel scientific inquiry for years to come. With each new discovery, we inch closer to a more cohesive understanding of the universe's origins and its ongoing evolution, igniting excitement for future explorations.